Hi everyone, here is the first laboratory for ETE335. This is a crossover network. This one specifically is made by Harman JBL speaker systems, and we will use this as a laboratory to gain familiarity, confirm information we already know about speakers and filters. The first thing you will notice about the crossover network is there are three connections, red, yellow, and green, shown in the picture. If you look at the data sheet, which you have access to, the red is the input to the crossover, the yellow is the high pass output, and the green is the low pass output. Each one of the inputs or outputs has a wire with a black mark on it. That signal is common to the input and output, so that will be your reference common for your measurements. We'll set up the experiment, which uses the arbitrary waveform generator and the oscilloscope, two channels on the oscilloscope. We'll set that up and continue. Okay, the connections have been made. On the input we have the signal from the arbitrary waveform generator, and the signal also goes to channel 2 of the scope. The output of the high pass, we're using the high pass RC filter for our test, goes to channel 1. The reason why we use channel 2 for the input signal is the scope reference is off as channel 2. Okay, now we will auto scale the measurement on the scope. There we see the display. Channel 1 is displayed on the top, channel 2 on the bottom. The channel 1 is the output from the high pass filter, channel 2 is the input from the generator. Now, we need to set up our generator for the appropriate range. We're going to set it up for 10 volts peak to peak and a frequency of 5 kilohertz. The 5 kilohertz is picked because it's very close to the critical frequency. On the scope, we need to do a couple things to make for a better display. First, push the acquire button and then select averaging. Averaging of 16 is good. It cleans up the display. And then set up your measurements. The three measurements we're going to be making are RMS of channel 1, RMS of channel 2, and phase between channels 1 and 2. I prefer to have my screens overlap, so I'm going to adjust the two signals so they directly are referenced to one another. Position those, and now we can see the phase shift more readily. Make sure that each one of the signals has the same magnitude for a better display. Here we see the scope display. The value of the phase shift is 40.5 degrees, which is very close to 45 degrees, which we expected at the critical frequency. So we know our measurement is fundamentally sound. At this point, we can then adjust the frequency on the generator to any value we want and take new readings. So we'll go down to 1 kilohertz. On the scope display, you will have to adjust the time base to get a better display, and you may have to adjust the channel 1 signal as the signal will change with frequency. Now we can get a good reading of the phase shift. Download the frequency information, the amplitude information from channel 1, channel 2, and the phase shift, and that's all you need for each frequency. It is useful to be able to acquire screenshots below the critical frequency, at the critical frequency and above the critical frequency. So 1 kilohertz is below the critical frequency for this high-pass filter. The critical frequency is around 4.2 kilohertz, so 10 kilohertz would be above the critical frequency. If we go to 10 kilohertz, we get a display from of the output and input. Match the two signals so they match in terms of amplitude, which is shown in the top left of the screen, and you're ready to go. Take frequency data for the high and low pass sections of the crossover filter. Yellow again was the high pass section, green will be the low pass section. Each one of them have an 8.2 ohm termination resistor. That's important for the filtering to work properly. And that is the first laboratory that you will be performing in ETE335.